Tonight, we travel back in time to a world where daily life was far stranger than you might imagine. Some of these habits may even surprise you. Imagine Earth as a spinning top, not perfectly upright, but tilted at an angle, wobbling ever so slightly as it spins. That wobble is real. Earth's axis doesn't point in a fixed direction through space. It traces a slow circle, like the handle of a spinning top, drawing lazy loops in the air. This motion is called axial precession, and it's so gradual that you could watch the sky every night of your entire life and never notice it happening. The wobble takes 25,920 years to complete one full cycle. During that time, the position of the star slowly shifts. The North Star, Polaris, our current celestial anchor, won't always be the North Star. 5,000 years ago, a different star, Thuban, marked true north. 5,000 years from now, it will be Alrai. The stars themselves aren't moving. We are. Our planet's axis is tracing that vast, imperceptible circle, changing our perspective on the cosmos degree by degree, generation by generation. The effect is most noticeable at the equinoxes. Twice a year, day and night balance at exactly equal lengths. Spring equinox and autumn equinox. On those days, the sun rises due east and sets due west. But which constellation sits on the eastern horizon at dawn, behind the rising sun, slowly changes. Right now, we're transitioning from the age of Pisces into the age of Aquarius. The sun at spring equinox is shifting from the constellation Pisces toward Aquarius. This shift takes about 2,160 years per constellation, 1/12 of the complete precessional cycle. Ancient cultures named these periods ages. The age of Taurus, when the spring equinox occurred with the sun in Taurus the bull, lasted roughly from 4,000 to 2,000 BCE. The age of Aries followed, from 2000 BCE to the start of the Common Era. The age of Pisces has dominated the past 2,000 years. Each age corresponds to which constellation, backdrop the sun rises against on the spring equinox. Here's why this matters. Precession moves incredibly slowly. It takes 72 years for the stars to shift just 1 degree. A single degree is barely perceptible, about twice the width of the full moon. To notice this shift, you'd need records spanning multiple human lifetimes. To understand the full cycle, you'd need continuous observation spanning thousands of years, maintained across the rise and fall of entire civilizations. Modern astronomy confirmed precession relatively recently. Hipparchus, a Greek astronomer, suspected something was happening around 150 BCE, comparing his observations to records made centuries earlier. But the full understanding came much later. Edmund Halley, in the 1700s, used precise instruments to definitively prove the stars were shifting position. Newton's physics explained why. The gravitational pull of the sun and moon on Earth's equatorial bulge causes the wobble. This was cutting-edge science of the Enlightenment era. Yet ancient cultures knew. They didn't just know. They tracked precession with remarkable precision and encoded it into their monuments, their myths, their most sacred knowledge. Egyptian texts reference the first time, a golden age associated with different celestial configurations. Hindu astronomy describes the precession cycle as the Great Year, dividing it into epochs called yugas. Greek myths speak of different ages: the Golden Age, Silver Age, Bronze Age, which some researchers interpret as allegories for precessional ages. The Bible contains zodiacal references that shift through different books: the bull imagery in earlier texts, the ram in later ones, the fish symbolism in Christian traditions. These aren't coincidences. They're markers of astronomical time, preserved in religious and mythological language. The ancient astronomers who tracked precession weren't observing casually. They were conducting a multi-generational scientific project that required institutional stability, dedicated record-keeping, and mathematical sophistication. They had to measure star positions with enough precision to detect a shift of 1 degree over 72 years. They had to maintain those records reliably for centuries. They had to understand what they were observing, that this wasn't random drift, but a predictable cycle that would eventually return to its starting point after 26 millennia. This is the cosmic clock ancient peoples learned to read. Not the daily spin of Earth, or the monthly cycle of the moon, or even the yearly journey of the sun through seasons. This is the vast, almost imperceptible rotation that measures time on civilizational scales. Understanding precession means thinking in terms of deep time, of patterns that emerge only when viewed across the spans of ages. And somehow, they did exactly that. The Great Sphinx crouches on the Giza Plateau, gazing eastward across the desert toward the horizon where the sun rises. It's been sitting there, according to Orthodox Egyptology, for about 4,500 years, carved during the reign of Pharaoh Khafra, around 2500 BCE. It supposedly represents the king's face atop a lion's body, a guardian for the nearby pyramid complex. The dating seems solid. Archaeological evidence places it in the Old Kingdom period. Inscriptions suggest Khafra's involvement. This is the mainstream consensus, taught in universities and published in textbooks. Then geologist Robert Schoch examined the weathering patterns. Schoch, from Boston University, wasn't looking to overturn Egyptian chronology. He was analyzing erosion, the physical process by which rock breaks down over time. And what he found on the Sphinx didn't match what should be there. The erosion patterns suggested water, not the wind-driven sand erosion you'd expect in a desert environment, but vertical weathering channels carved by rainfall. Heavy, sustained rainfall. Egypt has been arid for thousands of years. The Sahara's expansion turned the region into desert around 3000 BCE. Rainfall sufficient to create the erosion patterns Schoch observed would require going back much further, to the wetter climate that existed in North Africa between 10,000 and 5000 BCE. If Schoch's interpretation is correct, the Sphinx could be thousands of years older than conventional dating suggests. Egyptologists pushed back hard. They argued that water erosion could result from Nile flooding, from groundwater, from other moisture sources besides rain. They pointed to the complete lack of archaeological evidence for a civilization capable of carving the Sphinx 10,000 years ago. They noted that stylistic analysis places the Sphinx firmly in the Old Kingdom period. The debate remains contentious, unresolved, splitting along disciplinary lines. Geology versus archaeology. Physical evidence versus historical context. But there's another piece to this puzzle, an astronomical one. The Sphinx faces due east, precisely aligned to the sunrise point on the spring and autumn equinoxes. Its gaze is locked on that specific spot where the sun appears twice yearly when day and night balance. And around 10,500 BCE, right in the middle of the period when Schoch's geology suggests the Sphinx might have been carved, the constellation Leo was rising heliacally at spring equinox. Heliacal rising means the constellation appeared on the eastern horizon just before dawn, in the same spot where the sun was about to rise. The Sphinx has a lion's body. During the age of Leo, it would have been staring directly at its celestial counterpart, watching the constellation of the lion rise precisely where its stone gaze was directed. This alignment is called the Orion correlation theory, when extended to the pyramid. But the Leo connection is simpler and more direct. If you wanted to create a monument marking the age of Leo, you'd carve a lion facing east toward the equinox sunrise, where Leo was rising. You'd orient it precisely to that point. You'd make it permanent, built to last through subsequent ages as a marker saying, this was when Leo dominated the eastern sky at spring equinox. Proponents of the older dating see this as too perfect to be coincidence. Skeptics point out that you can find astronomical alignments in almost any ancient structure, if you look hard enough, and select your preferred dates. Orthodox Egyptologists note that the Sphinx's head appears to have been recarved at some point. It's proportionally too small for the body, suggesting it might have been reshaped during Khafra's time, even if the body is older. The controversy remains unresolved. But here's what's not controversial. Whoever built the Sphinx, whenever they built it, understood precession well enough to encode astronomical time into stone. Whether the monument dates to 2500 BCE or 10,000 BCE, it demonstrates knowledge of long-term celestial cycles. The precision of the eastward alignment isn't casual. It's deliberate, calculated, based on understanding how the sun's position shifts over vast time periods. The Sphinx may not prove ancient supercivilizations predating conventional history. It may not validate controversial geological interpretations. But it does prove that ancient builders thought in terms of precessional ages. They understood that the zodiac constellation rising at spring equinox was significant. They knew this position slowly changed, and they built accordingly, creating monuments that would stand as permanent markers of astronomical time. The lion faces east, watching the horizon where its celestial twin once rose. Whether that gaze was carved 10,000 years ago or 5,000 years ago, it was carved by people who understood the cosmic clock was ticking, measuring time in ages rather than years. They built something that would outlast their civilization, their language, even the memory of why they built it. But the astronomical message remains, encoded in stone, waiting for us to finally understand what they were trying to preserve. Angkor Wat rises from the Cambodian jungle like something from another world. Built in the early 12th century CE by King Surya Varman II, it's the largest religious monument on Earth. A massive stone temple complex, originally dedicated to the Hindu god Vishnu, later converted to Buddhist use. The central tower reaches skyward like a mountain made geometric, surrounded by galleries covered in intricate bas-reliefs depicting myths, battles, and celestial beings. Tourists visit by the thousands, photographing the iconic silhouette reflected in the rectangular pools that mirror its towers. But Angkor Wat is more than architecture. It's an astronomical instrument built to last millennia. The temple's causeway, the long approach that leads to the main entrance, is aligned with remarkable precision. Not due east, as you might expect for a sunrise-oriented temple, but 0.75 degrees south of east. This seems odd at first. Why the offset? But researchers studying the temple's orientation notice something fascinating. That slight deviation compensates for the Earth's axial tilt in a way that points back through time. If you account for precession, that alignment aims at where the equinox sunrise would have occurred during the age of Leo, the same period encoded in the Sphinx, roughly 10,500 BCE. The numbers embedded in Angkor Wat's architecture tell their own story. The temple's dimensions incorporate 72, the number of years required for 1 degree of precessional shift. Multiply 72 by 360 degrees, and you get the full precessional cycle. The number 108 appears repeatedly in the temple's design. There are 108 sacred sites around Angkor, 108 divine beings in various depictions. 108 equals 72 plus 36. 36 is half of 72, significant in the geometry of precession. These aren't random. They're mathematical signatures embedded in stone. The most striking astronomical encoding appears in the bas-relief called the Churning of the Ocean of Milk. It stretches along the eastern gallery, a massive stone carving showing gods and demons engaged in a cosmic tug-of-war. They're pulling on the giant serpent Vasuki, who is wrapped around Mount Mandara. As they pull, churning the cosmic ocean, Amrita, the elixir of immortality, emerges from the depths. It's one of Hinduism's central creation myths, beautifully rendered in stone. But researchers studying archaeoastronomy notice something beneath the mythology. The image depicts a twisting axis, the mountain wrapped by the serpent, being pulled in opposite directions, causing rotation. This is precession. The Earth's axis twisting slowly through its 26,000-year cycle. The pole star changing. The equinox points drifting through the zodiac. The churning produces different ages, different epochs, as the cosmic clock advances. The gods and demons represent opposing forces, but their cooperation drives the cycle forward. The serpent wrapped around the axis is the ecliptic, the path of the sun through the zodiac, twisting as precession causes the stars to shift. Mainstream archaeoastronomers remain skeptical. Complex monuments contain many numbers, many alignments, many patterns. If you look for specific numerical relationships, you'll find them whether they were intentional or not. The human brain excels at pattern recognition, sometimes seeing significance where none exists. Angkor Wat is vast and intricate enough that many numerical coincidences are inevitable. But the Khmer civilization that built Angkor Wat demonstrated sophisticated astronomical knowledge in other contexts. They tracked eclipses. They maintained calendars that synchronized lunar and solar cycles. They understood planetary movements. The temples throughout the Angkor complex align to various celestial events. Solstices, equinoxes, specific stellar risings. This wasn't a culture that randomly placed buildings. They planned with astronomical precision. An Angkor Wat was built in the 12th century, medieval times by Western reckoning. This wasn't ancient Egypt or prehistoric Malta. This was a period when European scholars were slowly recovering classical knowledge lost during the Dark Ages. Yet the Khmer were encoding processional mathematics into the largest religious monument ever built. This suggests something profound. Procession knowledge wasn't unique to Egypt or Greece. It wasn't discovered once and then lost. It persisted across cultures and centuries, passed down through traditions we're only beginning to understand. The Khmer builders who designed Angkor Wat inherited astronomical knowledge that stretched back thousands of years. They preserved it, encoded it, built it into stone that would outlast their empire. The temple still stands. The bas-reliefs still show the cosmic churning. The alignments still point through time to ages long past. And the numbers, 72, 108, the precise offset of 0.75 degrees, remain embedded in the architecture, waiting for observers who understand what they're seeing. 3 continents, 3 structures separated by thousands of miles and thousands of years. The Sphinx in Egypt, Angkor Wat in Cambodia, and elsewhere, from Britain's stone circles to South American temples, the same obsession with marking processional time appears again and again. Ancient cultures weren't just watching the sky casually. They were tracking the vast cosmic dance, measuring time in ages, preserving knowledge of cycles that transcend individual civilizations. Mathematics doesn't lie. 2 + 2 = 4 in ancient Babylon, medieval China, and modern New York. Pi is the same constant whether calculated by Egyptian scribes or quantum computers. Mathematical truth is universal, objective, verifiable. So when we find ancient cultures using sophisticated mathematical concepts, we can't dismiss it as cultural interpretation or symbolic meaning. Numbers are numbers. And the numbers ancient peoples worked with reveal capabilities that don't fit comfortably into our understanding of their supposed limitations. The Babylonians divided circles into 360 degrees. They divided hours into 60 minutes, minutes into 60 seconds. We still use their system today, 4,000 years later, because it works beautifully. But base 60 isn't intuitive. Most cultures count in base 10, 10 fingers, 10 toes, natural human counting. Base 60 is sophisticated precisely because 60 has so many divisors. You can divide it evenly by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This makes it ideal for astronomy and geometry, where you're constantly dividing circles, calculating angles, and working with fractions. Where did this system come from? The Babylonians didn't invent it from scratch. They inherited it from the Sumerians, who used it even earlier. But that just pushes the question back further. Why would early Bronze Age cultures develop a mathematical system this sophisticated? What need drove its creation? The Sumerians had words and written symbols for numbers in the millions. Not thousands. Millions. Their mathematical texts show calculations at scales that seem absurd for an agricultural society. Why would people tracking grain harvests and livestock need to think in terms of numbers reaching 7 digits? What were they counting that required mathematics at this level? Ancient Egyptians calculated the area of circles using an approximation of pi equal to 3.16. The actual value is 3.14159. They were off by less than 1%. The Rind mathematical papyrus, written around 1550 BCE, contains algebraic equations, relationships between unknown quantities that you solve through systematic manipulation. Orthodox history claims algebra was developed much later, formalized by Islamic mathematicians in the medieval period. Yet here it is, in Egypt, over 3,000 years ago, worked out in hieratic script on papyrus. Egyptian fractions used unit fractions, fractions with 1 as the numerator. They could express any rational number as a sum of different unit fractions. This seems limiting at first, but it requires sophisticated understanding of number theory and divisibility. The calculations work. The mathematics is sound. Egyptian engineers used these methods to build structures that still stand millennia later. And then there's the Ishango bone, found in Central Africa, dated to over 20,000 years ago. It's a bone with deliberate tally marks carved into it, 3 columns of notches, arranged in patterns that some researchers interpret as demonstrating awareness of prime numbers. Numbers divisible only by themselves and 1. Others see evidence of a lunar calendar, tracking the 29.5-day cycle of the moon. Still others argue it's a simple counting tool with no deeper mathematical significance. But even if the Ishango bone is just a counting device, it represents abstract mathematical thinking in the Paleolithic period. Someone was recording numerical information systematically, creating a permanent external record rather than relying on memory. That's a sophisticated cognitive leap. Externalizing thought, creating symbols that represent quantities, trusting that future observation will need reference to past data. These examples span continents and millennia. Babylonian sexagesimal mathematics, Sumerian large number systems, Egyptian approximations of pi, and algebraic problem solving, African tally marks from the Stone Age. They're not anomalies. They're a pattern. Ancient cultures engaged with mathematics at levels of sophistication that challenge our assumption of linear intellectual progress. The mathematics is verifiable. You can check the calculations yourself. The Rind papyrus sits in the British Museum. Babylonian clay tablets fill archaeological collections. The Ishango bone is housed in Belgium. These aren't reconstructions or interpretations. They're primary sources, original documents showing the actual mathematics ancient peoples used. The question isn't whether they did advanced mathematics. The evidence proves they did. The question is where this knowledge came from, how it developed, and why Bronze Age cultures possessed mathematical sophistication that we associate with much later periods of human history. The numbers don't add up. Not because the mathematics is wrong, but because the timeline doesn't explain how they learned it. The Great Pyramid of Giza is massive beyond easy comprehension. Originally 146.5 meters tall, a 40-story building in modern terms, constructed from approximately 2.3 million stone blocks, each weighing several tons, covering 13 acres at its base. Built, according to Orthodox dating, around 2560 BCE, during Egypt's Old Kingdom. It's the last surviving wonder of the ancient world. and it's been studied more intensively than perhaps any other structure in human history. And the more precisely we measure it, the stranger it becomes. The pyramid's base is aligned to true north with an accuracy of 3/60ths of a single degree. That's not approximately north. That's not close enough for ancient work. That's precision that modern construction projects struggle to match. Finding true north requires understanding that there's a difference between magnetic north, where compasses point, and true north, the axis around which Earth rotates. The ancient builders somehow determined true north to within a tiny fraction of a degree, and then maintained that alignment across a base covering 13 acres. But the alignment is just the beginning. The real mystery lies in the mathematical relationships encoded in the pyramid's dimensions. Take the pyramid's perimeter and divide it by its height. You get a number very close to 2 times pi. Pi, the ratio of a circle's circumference to its diameter. That fundamental mathematical constant equal to approximately 3.14159. The pyramid's semi-perimeter divided by its height equals 1.5708. Pi divided by 2 equals 1.57079. The match is precise to 4 decimal places. Is this intentional encoding or coincidental result of the pyramid's shape? The debate rages. Skeptics point out that the pyramid's slope angle, approximately 51.84 degrees, naturally produces these ratios. Choose that angle for structural or aesthetic reasons, and the pi relationship emerges automatically, without anyone needing to understand pi theoretically. The builders could have worked from simple geometric principles, perhaps using a wheel to measure distances, naturally incorporating circular ratios without consciously thinking about pi. But here's what makes dismissing this difficult. The precision appears in multiple ways. The pyramid's base perimeter, approximately 921.45 meters, divided by twice its height, gives 3.1428. That's within 0.05% of pi's actual value. For a structure built 4,500 years ago, using copper tools and rope, achieving this level of precision seems almost impossible by accident. Then there's the golden ratio. Phi, approximately 1.618, appears throughout nature. In nautilus shells, flower petals, galaxy spirals, human facial proportions. It's considered the most aesthetically perfect proportion, the divine ratio that produces beauty and harmony. Some researchers argue that the pyramid's dimensions encode phi in the ratio of its slant height to half its base length. Run the numbers, and phi emerges. Euclid wouldn't describe the golden ratio mathematically until around 300 BCE, over 2,000 years after the pyramid's construction. Did Egyptian builders understand phi and consciously incorporate it? Or did they work from empirical aesthetic judgment, building in proportions that felt right, unaware they were recreating a mathematical constant that governs natural growth patterns? Orthodox Egyptologists argue for simple explanations. The builders used ropes and measuring rods. They worked from practical geometry, solving engineering problems through trial and error, and accumulated experience. The mathematical relationships we see are artifacts of reasonable construction choices, not evidence of advanced theoretical knowledge. Give skilled craftsmen a few simple tools and clear objectives, and they can achieve remarkable precision without understanding the abstract mathematics underlying their work. Alternative researchers argue the precision is too consistent, appearing in too many ways simultaneously to be purely coincidental. The pyramid encodes pi, phi, precise alignment, and astronomical relationships. At some point, the accumulation of mathematical correlations suggests intentional design rather than happy accident. There's even the famous latitude correlation. The pyramid sits at 29.9792 degrees north. The speed of light in vacuum is 299,792,458 meters per second. The first 6 digits match. This feels almost too perfect to be real, except for obvious problems. The meter was defined in the 18th century. The speed of light measured precisely in the 19th century. And there's no reason Egyptian builders would encode a modern unit of measurement. They couldn't possibly have known. Yet the correlation exists. Whether meaningful or meaningless, the numbers match. The Great Pyramid stands as a mathematical puzzle. Every measurement produces new relationships, new ratios, new constants appearing in stone. Whether you interpret this as intentional encoding of advanced mathematics or as the natural result of skilled practical geometry, one thing remains clear. Ancient Egyptian builders achieved precision that challenges our assumptions about their capabilities. They built something that contains mathematical relationships we're still discovering and debating thousands of years later. The pyramid isn't just a tomb or a monument. It's a mathematical statement, carved in millions of tons of stone, demonstrating capabilities that don't fit comfortably into our boxes labeled primitive or pre-scientific. The numbers are there. The precision is real. What it means, that's where the mystery deepens. Isaac Newton published his Principia Mathematica in 1687. In it, he formulated the laws of motion and universal gravitation, the mathematical physics describing how objects move and how gravity governs celestial mechanics. These laws explained why planets orbit in ellipses, how tides work, why moons circle planets, and how to predict the exact positions of celestial bodies decades or centuries in advance. Newton's work represented a revolutionary breakthrough, the foundation of modern physics, the moment when humanity finally understood the mechanics of the cosmos. Except that ancient cultures were already using these principles millennia earlier, without ever writing down the theory. The Babylonians predicted lunar eclipses 50 years in advance. Not approximate predictions, precise forecasts that specified which eclipses would be visible from Mesopotamia and which would occur on the opposite side of Earth. Their predictions worked. Repeatedly. Reliably. For this to be possible, they needed mathematical models accounting for the complex interactions between Earth, Moon, and Sun. They needed to understand that the Moon's orbit isn't perfectly regular. It speeds up and slows down, affected by the Sun's gravity, pulling on it differently depending on its position. This is Kepler's second law. Objects in elliptical orbits move faster when closer to what they're orbiting, slower when farther away. Kepler published this in 1609. The Babylonians were using it in practice over 2,000 years earlier. Modern analysis of Babylonian astronomical tablets reveals sophisticated mathematical techniques. They didn't just record observations, they developed predictive models. They calculated mean motions and anomalies. They understood that planetary movements follow patterns that repeat over long cycles. Mars has a synodic period, the time between oppositions, when Mars and Earth are closest, that varies because both planets have elliptical orbits. The Babylonians tracked this variation accurately enough to predict future positions. How did they know planets don't move at constant speeds? You can't see that directly. Mars moves against the background stars. But detecting that its motion accelerates and decelerates requires precise measurement over long periods. Yet somehow they figured it out, incorporated it into their calculations, and made predictions that matched observations. Ancient Hindu astronomy demonstrates similar sophistication. The Surya Siddhanta, an astronomical text dated somewhere between 400 BCE and 400 CE, contains calculations for planetary orbits, their relative sizes, and their periods. The numbers work. The orbital periods given for Mercury, Venus, Mars, Jupiter, and Saturn are remarkably accurate. These aren't rough estimates. They're precise enough to serve as the basis for calendar calculations spanning centuries. The text describes how planets move in elliptical paths. It accounts for gravitational influences between celestial bodies. These are principles that Orthodox history credits to the scientific revolution, yet here they appear in Indian astronomical calculations over 1,000 years earlier. Then there's heliocentrism, the idea that Earth and other planets orbit the Sun rather than everything revolving around Earth. Copernicus gets credit for this in 1543, but the Greek philosopher Aristarchus proposed a heliocentric model around 270 BCE. His work mostly didn't survive. We know about it primarily through later writers mentioning his ideas. Some researchers argue that even earlier hints of heliocentric thinking appear in Vedic texts from India, though textual interpretation is complex and controversial. The question becomes, did ancient cultures understand the theory, or just develop mathematical models that happen to work? There's a meaningful distinction. You can create accurate predictions through empirical curve fitting without understanding the underlying physics. Modern machine learning does this constantly. Algorithms that predict outcomes without understanding why they work. But even that interpretation requires extraordinary sophistication. The Babylonians maintained observational records for centuries, developed mathematical techniques for extracting patterns from noisy data, created models accurate enough to predict rare events decades in advance. This is science, empirical, rigorous, producing verifiable results. Whether they had theoretical understanding of gravity or just mathematical models that worked, ancient astronomers achieved something remarkable. They predicted celestial mechanics with Newtonian precision, 3,000 years before Newton. The predictions are documented. The accuracy is verifiable. The physics underlying those predictions wouldn't be formally described for millennia, but the practical application was already there, carved in clay, computing the dance of worlds.